students, we're now on our next video on number theory, and in this video we're going to talk about the Euclidean algorithm, or not really the Euclidean algorithm proper, but the preliminaries that will lay the groundwork for the Euclidean algorithm. So as a sort of an introduction, there are several procedures that exist for finding the GCD of two positive integers. One efficient algorithm is what we call the Euclidean algorithm. This is it, named after Euclid, who included it in the book number 7 of his extraordinary work in the elements. The algorithm, however, was most likely known before him, but it lays the groundwork for the Euclidean algorithm. Okay, this theorem, okay, lays the groundwork of the Euclidean algorithm. So it is a fundamental tool in what we call now algorithmic number theory. So what does theorem number 5 state? We will just call it, for the sake in our videos, we'll call it theorem number 5, okay? In some other books, it may be called other numbers, by other numbers. So what does the theorem say? Let a and b be positive integers and r be the remainder. When a is divided by b, then therefore we say that the GCD, the greatest common divisor of a and b, is just equal to the greatest common divisor of b and r. Okay, so I think you can see here that a and b, this b here, okay, this shall we say the second number, okay, just became this one, okay, to the first number. Okay, so we will be looking at it in this way, okay, to give a proof. Actually, this will somehow be very similar to the Euclidean algorithm to give you a teaser of it. So GCD of B and R. You can imagine another GCD of R and something R. Let's call this the next number be Q. Say let's make it X. So notice here that what is happening, B is being chosen here, R is being moved here, and then so on. You can move on. And actually, this is the Euclidean algorithm until you can get the least number. Okay, until you can get the least number. But let's save the formula later. Let's save that for later. Okay, let me erase this. Make it bigger. Yeah. Okay, so let's give a proof for this here first. Okay, and then we will formally give the Euclidean algorithm. Okay, so for the proof. Okay, so we will let D be equal to the GCD of A and B, and um, D prime to be the GCD of B and R. Okay, so to prove D equals D prime, it suffices, to say, it suffices to show that D divides D prime and D prime divides D at the same time. If you can remember, this is theorem 1. This is theorem 1. So by the division algorithm, a unique quotient, sorry, a unique quotient Q exists, okay, such that A equals B times Q plus R. And we'll be using that equation later on. So first we want to show that D divides D prime rather. So to show that D divides D prime, we will first, okay, we'll first state that since D is equal to the GCD of A and B, okay, therefore we can say that D divides A and D divides B, since it's the GCD already. It's the greatest common divisor. But the thing is, it's common. Oops, it's common. So by theorem 4, so we say that D divides BQ. So this is by theorem 4, based on our videos. Theorem 4. Okay? But this is based on theorem 4. If you want to recall theorem 4, it states that if A divides B, then A divides a multiple of B. Let's call it BC. So in this part, D divides B, so therefore it divides also a multiple of B. That's BQ. Let's call it BQ. So that is why we use theorem 4. Okay, so therefore, then we then say after this theorem, B divides BQ. So then we say then D also divides A minus BQ. Now this is now by theorem 3. So what does theorem 3 states? Theory 3 states that if A divides B and the same time A divides C, then A divides the linear combination of this. So we have alpha B plus beta C. Okay, so what happened here? How did that happen, sir? So we saw that D divides A over here, and likewise D divides BQ over here. So meaning it divides a linear combination of this A and Q. So A we will just put alpha as 1. That's okay. Alpha as 1. And here in the BQ we put our beta. C here is just the BQ. We put the beta as minus 1. So that's why it became minus BQ. So yeah, hopefully it's clear why that happens. So moving on, in other words, we can say, in other words, we say that D divides R. How does this become R? Because A minus BQ is equal to R. So how did that happen, sir? So take a look at this. Let's transpose. R is equal to transpose BQ to the other side. So we have A minus BQ. Meaning this one, A minus BQ, is just equal to R. That's why D divides R. Okay? Now, since D divides R, okay, so since D divides R by this equation here above, okay, by this equation above, by the equation above, yeah, by the equation above. Okay, that's it. Yeah, that's the reason actually. So thus, oops, sorry. So thus, oops, thus, D divides B and D divides R. Okay, where can we see that? We can see it here. D divides B and D divides R. Okay, so we can say D divides the GCD of B and R. That is D divides D prime. Okay, D divides D prime, because since we know that D prime is equal to the GCD of B and R over here, we let that as D prime. So to highlight, here it is. Okay, so since D is divisible, or D divides, or D is a factor of the GCD of B and R, therefore we can say that D divides D prime. Okay, so this is the argument that we have shown here for D divides D prime. Actually, the converse of it, D prime divides D, is fairly similar to what we will be showing. But that is if we will be showing it. But I won't be showing it anymore. Maybe I can leave it as an exercise. So we can just say similarly. Okay, similarly, it can be shown that d prime divides d. So you can just use maybe you can use the same argument here, and I'll just leave it as an exercise. Thus, by theorem one, now what does theorem one say, sir? Theorem one states that um, if A divides B and B divides A, then they're equal. Okay, now by theorem one, D, okay, since D divides D prime and D prime divides D, we have D equals D prime. So that is, since they're equal, let's go back to their definitions, to what's the value of them. The GCD of A and B is just equal to the GCD of B and R. And that's what we want to prove. Okay, so I think we're enough for the preliminaries for the concept itself. After this, I'll be giving some exercises for you to see the application of this theorem. So yeah, thank you very much for watching. You can always rewatch and replay. And yeah, I'll see you soon for the next video. Okay, thank you very much.